Okay, the session 3 is science application of satellite laser engine. The chairs are myself and José Rodríguez. The first speaker is Jorge del Pino. The title is very interesting. Once in a lifetime experiment. SLR observations of the Apophis encounter, Friday, April 13, 2029. Jorge.
Okay, so dear colleagues, we have many presentations here with hard science, hard numbers, and so on. Moment, how to change the shadowization?
Leaving the laser. Yeah.
No, and to change the page?
Probably either of this. That's the other one.
No.
It doesn't work.
I think it was disconnected here because somebody loaded the presentation. Try now? Yes.
Okay, sorry. And this presentation is a little bit different because it's based in something that have been happening for 100 years or 150. You know, it's Friday night, and a group of young researchers and young professors go to a pub. And after the normal conversation about football, girlfriend, boyfriends, and job opportunities, they start talking about science, some, let's say, crazy ideas. And somehow we have some back of the envelope calculations, order of magnitude, some ideas. And this is the spirit of this presentation. Some ideas, back of the envelope, order of magnitude calculation, but no beer, sorry. And the question is the following. Why of the 100,000 plus asteroids we have in our solar system, we are talking about Apophis? The reason is the following. When this was discovered, for the first time was a high probability to crash against our planet. So this created the need to make a very precise orbit determination. And the good news that we have no chance of a crash for the next 100 years. But we have some facts that they are hard and real. First, we'll pass so close that we'll be closer to the geostationary belt. Second, the orbit will change. And third, this is not 100%, but the surface will change because of tidal forces. So the brightness, the so-called the albedo, and the color will change on real time when we are observing Apophis from the planet. Of course, for get this orbit, we need high-quality data. So the size of Apophis is well known. The albedo was found independently from the ESA satellite, and by photometry and radar observation, the rotation and the shape is also quite well known. So we know a lot of information about Apophis. So what I did was the following. I went to the Horizon system from NASA, and you can select Apophis from the database. You can put the coordinates of any station, set the time frame and the time interval, and send some settings. And I took two settings. Minimum elevation, 5 degrees, and should be at least twilight or night, because at the moment of the close approach will be night in Europe. And you know, science should be lazy, so I decided not to calculate all the European stations from the Eurolabs, so I created a polygon from the European, sorry, our colleague from Mexahovi. This is a Latvian presentation, so Riga should be present, and of course, Isanya is included. So what I found, this is the elevation against time, and you can see that for about over 2 hours, Apophis will be visible for all the European stations. The stations which are not included are in between all the stations of the polygon. This is the range. You see, with the radial velocity will be very high, but near the minimal approach will be quite similar. This is some opening. And you see for about 2-3 hours, the range will be quite similar, considering the distance. For example, between Golosiev in Kiev and Isanya, which is several thousand kilometers. And also, this Apophis will be very bright, will be magnitude 4 to 3. So visual guidance of the telescope will not be a problem. It's not guiding for LARES or a very small satellite, especially LARES 2. So it's clear that at least Eurolas can track Apophis, but we have the problem that we get a signal from Apophis. And we are now into the back of the envelope calculation. So using an analogy, I use the famous paper from Kirchner et al. About multi-static ranging. You know the idea, one station with a powerful laser is sending a beam, and the scattered photon, using probably this typical scattering, is received by the other. Of course, this is based on the SLR link equation. You know, this is this from the 2019 workshop as developed by Degnan. And of course, if you put all the numerical values, you get a fixed number of photoelectrons. But we are in the back of the envelope, so we can change this equation to the symbolic one, because we know that this experiment was successful. We know they got sufficient photoelectrons. We have a lot of parameters, and we have two parameters, the optical cross-section of the debris and the range to the debris or the satellite. And in the paper, the cross-section are given. I ran some calculation, and the typical range is 1,000 kilometers. So we get this kind of number. And you see, for this experiment, the coefficient 1 over square meter is in the order of 10 to minus 23. You remember we have some reliable data from Apophis. So if we plug Apophis into this experiment, we got this, 3 orders of magnitude less. So if this workshop have been 2 years ago, I never have done this presentation. But this year we got a couple of official press releases from 2 European institutions. One from ESA about the Isanya station. I will not talk, but you see in the development program, they plan to increase the power by 2 orders of magnitude. And the second about the Johannes Kepler system in Empfingen near Stuttgart. I don't know if you know about this, but this is a dedicated facility for space debris tracking. And by DLR, the goal is to observe 10 centimeters side debris for this range of height. So if they are planning to track until 2,000 kilometers, it's feasible, and this is included in the design to the system, you can track 10 centimeter debris and 1,000 kilometers. So we go to a similar symbolic equation from the Johannes Kepler, and using this parameter from the press release, this is the order of magnitude for the Empfingen system. And maybe you can remember for Apophis. And you see we have the same order of magnitude. So in principle, working on this order of magnitude working, theoretically, the Johannes Kepler system could get a return from Apophis. In the case, we have the mean radius and the maximum cross-section and so on. Of course, if we modify from B static, that the Empfingen is transmitted and the other station are receiving, there are 2 parameters for DB static which are important. One is the quantum efficiency of the receiving system and the mirror size. In 9 years, I hope all the stations will have high quantum efficiency in receiver with more or less a similar value. So the main parameter for the static will be the mirror size. More exactly, the relative aperture, which is related to the mirror size. And to make the history short, Grasse should get about 70% of the photoelectron from Empfingen, and down until Riga and Zimmerwald, we will get about 10-12%, and Borovitz will get about 3% of the photoelectrons. The other station will get below 1% of the data. So the static is possible, at least for several of the Eurolas stations. But there is another parameter. When you do this satellite static debris range, the angle between the transmitter and the receiver could be 90 degrees. So when you have this scattering, the energy depending on the incidence angle. But in the case of Apophis, this angle will be very slow. The maximum will be between Esanya and Kiev, of the order of 6 degrees. And for example, for the different combination, for example, Empfingen Riga or Matera Riga is 1 degree or 2 degrees. So the scatter light, the Lambertian scatter back to the receiving station will be of the same order of magnitude as the transmitting one. This is better than for normal space debris. So we have several questions. The first one, is we really can do an useful measurement to Apophis. Can we do it? What will the range bias? What will be the RMS? Could be used by the classical astronomical group, and how we can test it before Apophis is passing by. The other two are in the case it's not possible to do it, because many European stations, we are developing, for example, photometry, astrometry, etc. And also this can contribute to the Apophis observation. So this is an idea how could be a timetable in case it's possible to do it, starting now and until after 2029. So we will have about 5 years to make the proper calculation, the configuration of the experiment, as for funding is necessary, and maybe some testing if possible. But in any case, we need to make some calculation before that. One is because Apophis is elongated and rotated, will be necessary to have a precise model of the optical cross-section on the moment of the approach, including the Lambertian reflection at the surface. This is a very nice PhD thesis. And second, in order to distribute the roles between the stations, we need to know which station will be available during April. That means we need some reliable cloud cover statistic. We need to include the analysis centers at the beginning, because, for example, it will be very nice to segment the observation in half-an-hour block and to make a real-time CPF improvement during the observation. And also we have to take in account the wavelength, because not all the stations will be working at the green light. And by the way, in 2006 was a poster with some ideas about asteroid observation. You can go to the webpage and check it. And let's say this is a propaganda model. You know, for our previous presentation in Mexahovi and Riga, we are working in this cloud cover statistic. And here this is the last 5-year cloud cover analysis with 1 hour resolution. So my dream that this kind of analysis will be available for all the European stations, because this is very useful to planify some future experiment. So the first conclusion is not typical. Normally in the presentation you have a positive or a negative conclusion. This is a double negative. There is not a physical reason that is impossible to track Apophis. But of course we need to do the hard science, the hard calculation to make a real positive that is real possible to do it. And of course, this is assuming that we are using Apophis as a virgin asteroid. Up to now, all the missions, all the proposal to land something in Apophis has been rejected. A real reason, if there is no chance of a crash, there is no need to land, for example, a transponder or a frequency, a lighthouse or something like that. But you know, now we have private enterprise, and maybe Elon Musk or Bezos get the idea to land something on Apophis. So if anyone get the hint they are planning something, will be very nice to land either a laser retroreflector or some half a reflecting hemisphere to increase the signal. Something like cutting IGSI by the middle and putting into Apophis. And this will increase the chance of doing this observation. So this is the presentation in principle.
Thank you very much.
No, but this is not the end. And then you will ask the following: why I am doing this 7 years before Apophis? There are two reasons. One is personal, and the other is about the community. The personal is the following: 3 weeks after the Apophis encounter, I will be 80. That means I will be either retired, several years, or dead, or both. So my idea is to launch the idea that will be taken by the younger generation. For me, everybody under 55 is very young. It's a little boy. And to continue this job. Because maybe I will not be here in the planet to do this. And the second is something that will be a big discussion now. This is a very important field. This is not my field, space situational awareness, because this is not pure science. This is not applying science. This is protecting the space environment. And I have a question. How many of us use Google Maps today to be here? Can you raise your hand? So few. How many check the 7 days weather report to decide what to pack to be here? A lot of people. And you can imagine if we have the Kessler Center, remember this field gravity, no GPS, no MVSAT, no meteo data, nothing, because the natural resource of space will be fully destroyed. So it will be useful and interesting to have some kind of flagship experiment or mission that is so spectacular that will call the attention of the politician, which are giving the funding for doing research, the interest of the population, which are paying the taxes, that we are using the money for doing science, and the imagination of the small children that will be the next generation of scientists. Because if we don't go to the next step,
Jorge, you're going to have to leave it there.
This is the end. We will have a very big accident. Okay? Like this one. And this is all.
Thank you. Okay, because of the interest of time, only one question will be allowed. Yeah, but very nice talk. We are all impressed and superb imagination. I don't have an email address of Elon Musk, though.